Hi guys, Mohit here. This is part 2 of CUDA Graph series, and in the first part we talked about the basics of CUDA Graphs, like how normal CPU to GPU execution works, where kernel launch overhead comes from, how CUDA graph is created and reduces the repeated overhead. Now in this part I want to go deeper into where CUDA graphs are actually useful, especially in inference. So before starting with CUDA graphs, let's see how an LLM runs during an inference. Why certain parts of inference are good fit for CUDA graphs, or what problems we run into and how it deals with these problems. Let's understand what actually happens when an LLM generates a response. So let's say we give a simple prompt, for example, a capital of France is. The first thing that happens is tokenization. The prompt that I give is broken down into tokens that model can process. After that, the inference happens in two phases, which is a prefill phase and a decode phase. Now, during prefill, the model processes these tokens from our input prompt through transformer. This uses GPU operations like matrix multiplication, attention, normalization, and other operations across transformer layers. Now, while processing these tokens, the model also builds something called KV cache. For now, you can think of KV cache as a stored information about the tokens that the model has already processed. Meaning, this is important because when you generate new tokens, we don't want to recompute all the previous attention information from scratch every single time that we run. Instead, we store the keys and values from the previous tokens and reuse them during generation. So once the prompt has gone through the prefill, we now have processed our initial input and built a KV cache. Now the model produces the next token. In our current example, that will be Paris, because the current prompt that we have given. Now in the second phase, in decode, during the decode phase, the model generates new tokens incrementally, meaning for each decode step, we process a new input token through the model while reusing the information already stored in the KV cache. Okay, the model produces the next token, the KV cache is updated with the new tokens information, and then we run another decode step. This whole process repeats until the model finishes the generating the responses. Here is an animation that I've created. You can see I will run the fastest one first to show how the whole process actually works. Yeah, so if I slow it down and then I say, so this is our original prompt. This is the tokenization that we're doing. Prefill, updating the cache, use the current token, decode the next and predict the next word, which is Paris, and then update the KV cache for it, and then show us the output. So what we got from here is prefill processes the initial prompt, and decode is a repeated generation loop that produces new tokens incrementally. Now that you understand how inference works, let's zoom into a single decode step. When I say the model runs one decode step, that doesn't mean we are launching just one GPU operation. A transformer forward pass consists of many GPU operations. We have operations like query, key value projections, attention, output projections, MLP layers, etc., etc. Under a normal execution, the CPU has to keep up submitting the work, meaning the CPU submits a kernel, GPU executes it, then more work gets submitted, then the next kernel execute, and this continues throughout the decode step. And we're not doing this just once. We are repeating the decode process again and again as we generate new tokens. So especially in workloads such as small batches or latency sensitive inference, the CPU may not submit the work fast enough to keep the GPUs continuously busy. If we look at the timeline here, you can see the problem. Without CUDA graphs, the CPU repeatedly dispatches the GPU work. Between some of these operations, we can end up seeing the gaps where the GPU is waiting for more work to arrive. And this is where CUDA graphs actually become very useful. If you have a repeatable sequence of GPU operations during decode, CUDA can capture that sequence as a graph, meaning instead of CPU repeatedly submitting every captured operation individually on every replay, it can launch the prepared graph with much lower repeated CPU submission overhead. Now, if we check the other timeline, The GPU kernels didn't become faster. The attention isn't faster. What changed is the overhead around launching that work with the graph replay. The GPU operations can be submitted much more efficiently, reducing the CPU side launch gaps and allowing GPU to stay busier. So during LLM decode, where we repeatedly executing the similar GPU work for every generation step, that reduction can become very important. And here is a animation that shows it visually. You can see there is multiple kernel launches causing this minor gaps, and with the CUDA graphs there is just constant kernel launches and saving you a lot of time compared to the non-graph versus with the graph. So now we know why CUDA graphs can help during decode, but what exactly are we capturing and replaying? The easiest way to understand this is to separate two things: the execution structure and the data. When we capture our GPU work, CUDA records the sequence of operations and dependencies between them. For example, here we have operations like rope, KV, write, attention. That captured execution structure stays the same during the replay. But the data those operations work on can change. For example, look at our input token. We start with the. When we move to the next decode step, our input changes to the cat, then sat, and then so on. Our KV cache write position also moves forward as the new tokens are processed. But what's staying the same is we are still replaying the same captured sequence of GPU operations. So instead of rebuilding and resubmitting all of that GPU work for every decode step, we update the necessary data and replay the prepared graph again. The main and simple idea is the execution structure stays mostly the same, while the data changes between decode steps, but this creates a problem. LLM inference is naturally dynamic. So the KV cache changes, there is sequence length growth, and active request can change. So how can a mostly static graph handle all of these changing state? So now we have a problem. CUDA graphs want important parts of the execution to stay predictable, but during LLM inference, our sequence keeps growing and KV cache keeps changing, right? One way modern inference systems handle this is with paged KV cache and indirection. Instead of treating the KV cache as one of continuously growing block of memory, we divide it into a smaller physical blocks, and then we use something called block table. So the block table maps the logical blocks of our sequence to whatever their KV cache data lives in a physical memory. So as we generate more tokens, we can update this mapping and allocate new KV cache blocks when needed. The physical allocation of the data can change, but the attention kernel can access it through the indirection. Instead of needing the entire execution structure to change, this is one way dynamic KV cache state can still work with CUDA graph replay. But now the important question is, does all of these changes and fixes and implementations actually make the inference faster? Now let's actually visualize where the improvement comes from. Here, both sides are generating the same number of tokens and doing the same GPU computation. The difference is the time spent per decode step. Without CUDA graphs, we keep paying the repeated CPU launch overhead for every step. But with graph replay, we reduce that overhead so each token can be generated in less time. That small amount of time saved on one token gets saved again on the next one and then again on the next one. So as we generate more tokens, those repeated savings add up. This can give us lower latency per token and higher token generation throughput. The important thing is that CUDA graphs didn't make the actual model computation faster. We reduced the overhead around the computation, and because of the decode repeats this process token after token, even a small saving per step can become a meaningful improvement over the full generation. So that's it for this part of how CUDA graphs work with inference. There is a last part that I will upload in few days, which I will cover few more advanced topics and how it works with SGLang or VLLM. Thanks for watching.